Hi everyone, welcome to my poster. My name is Lan. I am a PhD student in North Carolina State University. PFAS are persistent contaminants with adverse environmental and public health effects. It has been detected globally in drinking water systems. An efficient PFAS treatment method is required in order to reduce the oral uptake of PFAS from our drinking water. Right now, the most widely used method for determining the ion change resin performance is field scale tests, such as pilot tests. However, pilot test is very time consuming and expensive. The rapid small scale column test is a bench scale test that can significantly reduce time and cost in the field scale test. However, a suitable scale up approach is not available. In this research, we are trying to develop a scale-up approach that can predict PFAS removal in field-scale IX contractors from a bench-scale test. We're also trying to investigate the effect of IX properties, water characteristics, and PFAS structures on IX performance. Now, let's look at the material and method part. The major step of this research starts with crashing the as received ion change resin into 200 by 230 US mesh size. Then we scale down the dimensions from the pilot test based on the assumption that the pore and surface diffusivities are constant with the particle size. Then we set up the RCT, and the PFAS samples was quantified in a triple plot. Now let's look at the result. The first four figures compares the breakthrough of RCT data and the pilot data. As can be seen from the first figure, the RCT underestimates by half the capacity of X resin in field scale in the pilot test. If we scale up the RCT data by doubling the breakthrough batch volumes, the RCT data matched up with the pilot data. The same conclusion was found from a different water and also a different ion change resin. One possibility of this phenomenon could be that we lost some of the capacity during the grinding. So in the future experiment, we will measuring and comparing the theoretical X capacity between the as received ion change resin and the crashed ion change resin. Except that we also investigate the effects of X property and the competing ions and water quality on X performance. So for the two tested ion change resin B, which is macroporous, was more effective than resin A, which is gel type. And then the nitrate in water matrix negatively affect PFAS uptake, while chloride and sulfate showed little effects. For the effects of TLC, we found the IX use rate increased with increasing TLC for PFAS that breaks through later, but also not strongly impact for PFAS that breaks through early. This finding was applied for both ion change resin we tested. Then from the RCT data, we investigated the effects of PFAS functional group and PFAS and chain length on X performance. In this figure, we can see that for a given chain length, PFAS with sulfonic acid group was more effective than PFAS with carbolic acid groups. For example, PFBS has higher batch volume at 15% breakthrough than PFPEA. And also we find that for a given PFAS subclass, for example, PFCAS, the X resin use rate decreased with increase in PFAS chain length. And also we found the insertion of one or more ethyl oxygen atoms. For example, here the branched PFECAS and the linear PFECAS. The insertion of ethyl oxygen decreases the removal of PFAS. That's the major point from my poster. If you have any question, please don't hesitate to ask me. Thank you. Here's my contact information. Thank you.